He's by himself. All year. And just so you guys know, your seats are, once we really get started, your seats are really more suggestions than like actual, I want you to work with who you want to work with. Not like, your groups are your groups, but like, when we're doing problems, if Katie wants to go over there. Alright, anyway, motion in one dimension. So it's motion like back and forth in a straight line. First thing we'll talk about here is distance versus displacement. So distance is how far you actually went. So that would be the blue line if you like walked from point A to point B and took this path. The blue line would measure the distance you walked. Does that make sense? Displacement is how far you started, so how far you are from where you started. So it's the red line from A to B is your distance. Does that make sense? So for example, if I walk 5 steps this way, turn around and walk 3 steps back this way, what's my displacement in terms of my steps? 2 steps. Make sense? Alright, speed versus velocity. Speed is a distance per unit of time. Velocity is speed plus a direction or displacement per unit of time. So speed is just going to be like how fast you're going. Velocity is how fast you're going in a certain direction. So for velocity, you're going to need a direction. A lot of times they're used interchangeably in problems, like in a straight line problem, if you go, going 5 meters per second, the direction doesn't really matter as long as you're not changing direction. Does that make sense? So you can kind of use them interchangeably, but know what the difference between them are. Units for both are meters per second, and velocity is abbreviated with a lowercase v. Everybody okay with that? Ben, you look like you're having a great time seeing this for the second time.
It's been a long day.
Alright, instant speed or instantaneous speed is how fast you're going at any given instant. Average speed is how fast you're going over the whole trip. So that's just distance over time for average speed. Alright, so speed and velocity questions. What is the average speed of a cheetah if it sprints 100 meters in 4 seconds? Julius.
25 meters per second.
You're amazing. How about if it sprints 50 meters in 2 seconds? 25 meters per second. Alright. You start from rest and accelerate to 80 kilometers per hour. Would it be possible to have an average speed of 80 kilometers per hour if you never traveled faster than 80 kilometers per hour? Tom?
No,
Nope. Why not?
because you can't accelerate to that instantaneously.
That's correct. So while you're accelerating, you're not going 80 miles per hour. So if you can travel 80 miles per hour after you do that forever, your average speed will always be something less than 80 because there's a time when you weren't going 80 miles per hour. Does that make sense? Right. The speedometer of a car moving east reads 100 kilometers per hour. It passes another car that moves to the west at 100 kilometers per hour. Both cars have the same speed. Yes. Both cars have the same velocity. No. Different directions. During a certain period of time, the speedometer of a car reads a constant 60 kilometers per hour. Is the car moving at constant speed?
Yes.
Yes. Is it moving at constant velocity?
Not necessarily.
Not necessarily. We don't know the answer to that. Alright. In a drag race, is it possible for a car with the greatest speed at the end of the race to lose? Yes. If one accelerates very quickly to a lower speed, it'll win the race over a car that accelerates very slowly to ultimately a higher speed. Does that kind of make sense? Right, does the speedometer of a car measure the instantaneous speed or the average speed? Instantaneous. Okay, if a duck had an average velocity of 0 meters per second over a time of 3 minutes, what can you say about its displacement?
0 meters.
0 meters. What can you say about its average speed? Nope. We know its average velocity was 0 and its displacement was 0. Does that necessarily mean it didn't move? So it could have either stayed in one spot or gone around in a circle. So you don't know anything about its average speed over that time. Does that make sense to everybody? Okay. So this is a fun one. You're riding your bike on a 10-mile long path. You travel the first 5 miles at a speed of 5 miles per hour. How fast do you have to travel over the next 5 miles for your average velocity to be 10 miles per hour? Nope. Ben or Katie, do you remember the answer to this one?
No, it's been too long.
Okay. Me talk. Time you gotta
Is it like instantaneous or like?
infinitely
Really-
fast.
really-
Like you have to do it in 0 time for your average speed to be 15 kilometers per hour. Or for 10 miles per hour. So I'll talk you through why here in a second, right now. So what's the total distance you're going to travel here? 10 miles. So our total distance is 10 miles. How long do you have to cover that distance of 10 miles if you want your average speed to be 10 miles per hour? 1 hour. So your time has to be 1 hour. So for your average speed to be 10 miles per hour, you need to cover that 10 miles in 1 hour. How long did it take you to cover the first 5 miles? An hour. So how much time do you have left to cover the second 5 miles? 0. Everybody understand that? So it matters when you're calculating like your average velocity. The distance you're traveling at a certain velocity matters less than the time you're traveling at that velocity. So if you traveled 1 hour at 5 miles per hour and 1 hour at 15 miles per hour, then your average would be 10. But if you traveled 5 miles at 10, or 5 miles at 5 miles per hour, and 15 miles, and 5 miles at 15 miles per hour, your average is not 10. So if the time is the same, then you take the halfway point between the numbers. But if the distance is the same, it doesn't work, because the time's not going to be the same. Because which are you spending more time doing, going at 5 or going at 10? Or going at 15? Yeah. Does that make sense, everybody? Alright. Since velocity is changing position per unit of time, what do you think the equation for velocity is?
Displacement over time.
Displacement over time. Alright, we'll go through acceleration, then we'll be done for the day. Alright, acceleration measures the rate at which velocity changes. And so acceleration equals the change in velocity over the change in time. So if you accelerate from 5 meters per second to 10 meters per second in 1 second, it's the change in velocity should be 5 divided by the time should be 1, so your acceleration would be 1 meter per second per second. So because acceleration usually involves a change in velocity, change in direction will also cause there to be an acceleration, and we'll cover that when we get to rotational motion later on this year. And the units for acceleration are meters per second, but usually that's written as meters per second squared. So what acceleration really means is you're accelerating like acceleration of 1 meter per second squared means every second you're going 1 meter per second faster. Does everybody kind of understand that? And acceleration is abbreviated with lowercase a. Okay. A particular car can go from rest, so 0 meters per second, to 90 meters per second in 10 seconds. What's its acceleration? So shout out answers if you. 9 meters per second squared. Okay, in 2.5 seconds, a car increases its speed from 60 kilometers per hour to 65 kilometers per hour, while a bicycle goes from rest to 5 kilometers per hour. Which undergoes a greater acceleration? Same. The change in velocity is the same for each. What is the acceleration of a car that drives past you at a constant velocity of 400 kilometers per hour? 0. Which has the greater acceleration? An airplane that goes from 1,000 kilometers per hour to 1,005 kilometers per hour in 10 seconds, or a skateboard that goes from rest to 5 kilometers per hour in 1 second? Skateboard. Can an object have a westward acceleration while traveling east? Yes. What's it doing then? Decelerating or slowing down. Does that make sense to everybody? So if you're traveling east and accelerating west, that means you're slowing down. So if your acceleration and your velocity are in opposite directions, you're slowing down. Make sense? And usually if that's happening, you can make either one negative, but usually we'll be making your acceleration negative when it's decelerating. Can an object be increasing its speed as its acceleration decreases? Yes. What's going on then?
It's still being faster, but just at a slower rate.
Yep. So it's going fast, still going faster, but the amount of the velocity increases each second. It's getting smaller. So if the first second you're accelerating at 5 meters per second squared, the next second you're accelerating at 4 meters per second squared, your velocity is still increasing, even though your acceleration went down. You guys understand that? Right. Since acceleration is change in velocity per unit of time, what would the equation for acceleration be?
Equals v over t.
Change in velocity over time, so it's going to be delta v over t. So the change in v over t, that's the change in v is going to be the final velocity minus the initial velocity. You'll get that equation here at some point. Alright, we'll go over the equations tomorrow. Alright, let's take the last 15 minutes and look at some of your science questions. Alright, so the first one here is about time travel. So is time travel possible? Yes, we're all traveling through time right now. And it's actually possible to travel through time at different rates. The faster you go, the slower time goes for you. Does that kind of make sense? No, some of you guys have probably heard this conversation before, but so let's say Emma's parents decide to go on a trip into outer space near the speed of light, and time, like the rate time slows down is relative to the speed of light. So if they took a trip to space at near the speed of light, if they went fast enough, it'd be like a year went by for them, but 50 years went by here on Earth where we are moving slower. So they'd come back, and Emma would be older than them. So, and the nearer you get to the speed of light, more time slows down. And it's usually we're talking like 99% of the speed of light before you see any really effects at all. And this is a well-proven theory of science, and they use it actually in practical applications as well. So like GPS systems would not be nearly as accurate if relativity wasn't calculated, because the electronic processes in the satellites that cover the GPS systems are happening slower than they would on Earth. Does that make sense? And it's not a huge, it's like a couple nanoseconds different, but it's enough to like change where they think the position of like a car is or something like that. Does that make sense? Now, so it's easy to go forward in time at whatever rate you really want if you can go fast enough. Going backwards in time is probably what you're more interested in, and there's more of a problem. The equations for special relativity break down at the speed of light. So like you gotta take the square root of a negative number actually at that point. So you get imaginary time for like how much time is passing. And some people say you go backwards in time because you get a negative time, but you have to take the square root of it, so you get, it just doesn't work. So, and there's a reason we can't go faster than the speed of light. In addition to time slowing down the faster you go, you behave as if you have more mass the faster you go. So as you go faster and faster, it gets harder for you to go any faster. And at the speed of light, your mass would, like, have you guys talked about limits in calculus yet? No, probably not. You will soon. But as you get closer to the speed of light, the mass you have, or behave like you have, goes toward infinity. So you also get skinnier as well as you go faster, but that's kind of a... Yes?
I don't know where I heard this, but heard something like if you could go faster than the speed of light, or if you would, then you would technically be going back in time, or you'd be traveling backwards in time.
No, like I said, the equation breaks down at that point because you get a negative value that you have to take the square root of. So like time equals the square root of -1 or something like that. So you get an imaginary number returned. But like you would like, you get the square root of a negative, so it seems like if you kind of continued the pattern, time slows, and it goes as close to 0 as possible as you get closer to the speed of light. So as you approach the speed of light, the time that passes for you is close to 0. So if you went past that, it kind of makes sense you'd go into negative time and start to go backwards in time. Does that make sense? But again, like, we don't understand, we don't think it's possible to go faster than the speed of light, and if it is, we don't understand what would happen, is the correct answer. Does that make sense, everybody? It's possible you go backwards in time, but we don't know for sure. It would be kind of very weird to see, because you'd like, how Einstein came up with this theory is he thought about like a clock tower sitting in, like, you know, the old like big clock towers with a clock in the middle. Think about traveling away from that clock. If you're traveling at the speed of light, you're seeing the same light over and over again, because that light's traveling with you, so the clock would never move. So if you traveled faster than the speed of light, you'd start seeing light that had passed you already, so you'd see the clock moving backwards. Does that kind of make sense? So another interesting side note to this is, because it takes like time to travel, which we don't like have a sense of here on Earth, but the sun, as we're seeing it, is 8 minutes older than we're seeing it. So we're looking 8 minutes back in time when we see the sun. When we see the closest star to us is 5 light years away. So we're looking at that star as it was 5 years ago. The majority of the stars you see at night are at least 100,000 light years away. You guys know what a light year is? It's how far light travels in years, measured distance. So if it's 1,000 light years away, when you see that star, you're seeing it as it was 1,000 years ago. So you look up at the stars at night, you're looking backwards in time, usually a significant amount. And the farthest stars in our galaxy from us are about 100,000 light years away. So if we look at a star like as far away as we could in our galaxy, we're looking at it was 100,000 years ago. And some of the things we think of as stars in the night sky are actually galaxies. If we look at one of those galaxies, they're at least 1 million light years away. And so you're seeing that galaxy as it was 1 million years ago. So if somebody in a distant galaxy, like that was 65 million light years away, what would they see on Earth? If they're looking at it, they'd see dinosaurs. And so when you look at those stars at night, some of those stars that you're seeing have gone out already. The light from their death just hasn't got to us yet. So the sun could have died, and we won't know for 8 minutes. If it died this instant, we wouldn't know until 8 minutes from now that the sun disappeared. Hey, any other questions related to that while we're... Are you guys done for the day? Alright, we'll be done for the day. So tomorrow we're going to finish these notes, and Friday we'll probably start the problems for this chapter. Oh, Kevin, this is fun. Kevin wrote down a question earlier that I saw that I didn't get a chance to answer. What are quarks? You guys will like this. Do you guys, anybody in here know what quarks are?
Isn't that what makes
That
up
will mix up
neutrons and protons?
Neutrons and protons. Up and down quarks makes up neutrons and protons. Ooh, I wonder. Okay, let's see if I can find it. So there's actually 6 types of quarks, and this is a song about them. It's really, let me plug in the, it's really dumb. You guys get a kick out of it though, and you remember what all the quarks are.
A quark is a fundamental constituent of matter, observed in 1968 when people asked scattered. We found that protons aren't as simple as we thought. We thought they were solid particles, but they are not. Protons, in fact, are made up of 3 separate pieces. It just gets more confusing as our knowledge increases, but that is what a quark is. It's a piece of a proton, and they also make up other things, including a neutron. Oh, that strange charm. Got 'em. If you don't know what a quark is, it don't matter. You still got 'em. And with electrons and protons and something from this, they make up everything that we can see and nothing that exists. It's made up of quarks, including protons and neutrons, are composite particles that physicists call hadrons. Many types of hadrons are theoretically described, but most exist for only very brief amounts of time. part, electric charge, color charge, mass and spin. And having color charge exists solely inside of other kinds of particles and cannot exist alone, which is why quarks have never been studied on their own. Up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter, you still got them. And electrons and photons, unless something is missed, they make up everything that we can see and that we know exists. Quarks can join together in two different ways. Baryons and mesons, but most instantly decay. If a particle has three quarks, then it's a baryon. If there's one quark and an anti-quark, then it is a meson. These tiny bits of matter are part of almost everything, and there is no unified theory to make it less confusing. But the fact that we've identified that they exist at all is so goddamn remarkable that I just sit in awe. Oh, up, down, strange charm, top, bottom. If you don't know what a quark is, it don't matter, you still got them. And with electrons and photons, unless something is missed, they make up everything that we can see and that we know exists.
My mind just got doubled in like 5 minutes.
So what are the 6 types of quarks?
Boom.
Left side, strange.
Up, down, strange, charm, top, bottom. So you guys will probably remember that forever now. Up, down, strange, charm, top, bottom.
Really?
That's not real.
What? It's not real.
Let's name it
I
charm.
thought those a lot.
Why not?
They were just saying.
There's actually a property called charm, and a charm quark has a charm of +1. There's a property called strange as well. And a strange quark has strange of +1.
So there's something that's
Nona, explain my free.
There is something. There's something inside a quark has a name, but it's never been discovered. I can't remember what the name is.
so there's something that's inside.
It's a proposed particle that would be inside of a quark, and it has a name, but it's never been observed. Yeah.
So how do they
Non-existent.
something that they don't know?
Maybe it's already been.
Quarks.
Yeah.
It comes from, it's a James Joyce novel, and I can't remember what it comes from. It's a literary reference, is what a quark is from. How they discovered them is, you guys know what a particle collider is? So it's those big things underground, they're a big circle underground. You've probably seen pictures in textbooks and stuff like that. What they do is they use magnetic fields to accelerate protons very quickly to each other. So they get the protons near the speed of light and then smash them together. And they do something called a cloud chamber, which is like a gaseous mixture. And when they collide, they leave trails in this cloud chamber that they can see under like magnified. So they smash 2 protons together and they see 6 little trails of things. And because it's in an electric field, they can figure out what the charge of those things are and approximately the mass of what they are with those cloud trails. So that's how they discovered quarks. But they only exist inside of something else, kind of like the song said. So as soon as they leave the proton or the neutron, they almost immediately disappear. So they can't exist by themselves. What
happens to that mass?
turns into energy? Mass, the conservation of mass is a horrible, horrible lie. From chemistry. Mass is only conserved in chemical reactions. In nuclear reactions, it is not conserved. Mass and energy are always conserved. So if mass can turn into energy and energy can turn into mass, and that quantity is always conserved, and that's the equation E equals mc squared. So the energy you get from, like if you lose 1 kilogram of mass, it's that mass times the speed of light squared will give you the amount of energy that's gained. Yeah.
What's an example of energy turning into mass?
Energy turning into mass, during the start of the universe, there was only energy. And, gosh, I can't remember, I don't think this experiment has been done. I think it has now. They take 2 high energy lasers and essentially point them together, and you'll get a proton and an antiproton. So if you have 2 high enough pieces of energy, like radiation, when they collide, they'll form a proton and an antiproton, or an electron and an anti-electron. One of the big mysteries that we don't know, because in the early universe, all this stuff was energy, and it all converted into protons and antiprotons, and electrons and anti-electrons.